Assalamualaikum warahmatullahi wabarakatuh. Welcome to another computer science lecture for 9618A2, paper number 3, Advanced Theory. Today we'll be starting our discussion on chapter number 15, Hardware and Virtual Machines. Specifically, we'll be discussing 15.1, Processors, Parallel Processing and Virtual Machines. The first thing we have to discuss is instruction set architecture. Now, before we get down to the details, there's something that you should know. Every processor that is made, or every model of the processor that is made, it has slightly different physical architecture. An Intel processor, an AMD Radeon processor, or a Macintosh processor, or a Mac processor, they would have the same components technically. All of them would have buses, all of them would have system clock, all of them would have MDR, MAR, and so many other registers, but their location, their interaction with each other would be different. This is the physical construction or the physical architecture of a microprocessor. But over here, I just told you that to clear your concepts, but technically we are not concerned with the physical architecture of a microprocessor. We are concerned with the logical aspect that is known as an instruction set architecture. Like what type of keywords, what type of instructions can be, or it's better to say if I explain it in a way like how if a instruction is given to a microprocessor, how a certain microprocessor or in what way it will be processed by the microprocessor. Technically, that is known as instruction set architecture. Now, before we go further, remember that a CPU's performance can be optimized in one of the two ways. Now, I'm not talking about the 5 factors you studied in your O-levels and AS that increase the bus size, increase the RAM and blah blah blah. No, we are talking in with the link of instruction set only, and for that there are only two things that you can do. You can either reduce the number of instructions per program or per code or per software, like write less number of instructions so they can be processed more quickly in order to perform a task, or minimize cycles per instruction, like reduce the time that is dedicated per instruction so all the instructions can be processed in a lesser time. Now, following are some of the types of processors according to instruction set architecture, not physical architecture. Well, it has something to do with the physical architecture as well, but physical architecture of a computer system, of a microprocessor, is not really a part of our syllabus. So anyways, hopefully you get the idea. The first type of processor we have in our syllabus is known as reduced instruction set architecture. 15.1 is kind of an important because usually you get something like one question of about 2 to 4 marks in, if not every paper 3, then every other or every second paper 3. Either sometimes it is from RISC, reduced instruction set, sometimes it is of any other, but there is usually one question. Anyways, RISC is the abbreviation, like I just told you, reduced instruction set computer, where you try to reduce the number of instructions. You make hardware as simple as possible by employing an instruction set that only contains a few basic steps, and by using those basic steps you try to process all the information. A load command over here, basically instructions are very simple. If you say load, then only data will be loaded. If you say store, data will be stored in a specific register. A single command cannot perform two things. Characteristics of RISC architecture: it has simpler instructions and simple instruction decoding. The processor does not take too much time in trying to understand what is being written in the code. More general purpose registers, because you have to basically you have simpler instructions to do. The instruction takes one clock cycle in order to get executed. So no matter what type of instruction you have, typically an instruction set has something like 1500 to 2000 instructions or keywords. Any one of them in a RISC processor takes exactly one clock cycle. So basically, if you have a 1.2 gigahertz processor, that means it can process 1.2 billion instructions of such type, and you get the idea. The instruction comes under the size of a single word. Like instructions aren't complex. Pipeline can be easily achieved. Pipelining is a technique used by processors where every instruction is broken down into multiple stages, and this allows the end goal of that is multiple instructions can be processed simultaneously. Few data types are available in RISC processors and simple addressing mod. There is no complexity in addressing mods. Then we have complex instruction set computers. This is that in this type of computers, a single instruction will handle evaluation, loading, and storing operation. Basically, you can say a single line of code or a single statement of code can perform multiple tasks. That's why it is known as complex instruction set, or it is complicated. Characteristics of CISC: instructions are complex, they are not simple, and thus they need a complex decoding mechanism. Decoding means translation into pure binary. The instructions may take more than one clock cycle because obviously you're trying to perform multiple tasks in one instruction. Instruction is larger than one word size. Obviously, if you're trying to do three things or command three things in a single sentence, you cannot just do them with one single word. Like if I want you to run and run in a zigzag pattern, the most simple thing to do would be to just say run. And a little complex would be or something like run in zigzag. I cannot use single words to give you complex instructions. If I am giving you multiple instructions that you have to run, but you have to shift on your left and right as well while running, this is a complex task technically. So for that, I have to use more words in order to explain what my intention is. So that's why in a CISC computer or processor, instructions are almost never a single word. They always contains 2 or 3 words. Lesser general purpose registers cause the operations get performed only in the memory. It has more data types cause it can perform slightly complex operations, and it has complex addressing modes because technically everything is connected with each other. Both CISC and RISC approaches try to increase the performance of a CPU, but here's a fundamental difference between them. CISC tries to minimize the total number of instructions you have to write, because if in every line you can give 2 or 3 commands or 2 or 3 instructions, then the size of the code will be less. Whereas RISC tries to reduce the number of cycles or the time taken by each instruction, because instructions are simple, so one instruction only takes one clock cycle. In order to try to minimize the total number of the total time taken by your program, because if you are able to reduce the cycles per instructions, then ultimately the cost for the resources needed for processing the entire program will be lesser. This is a simple diagram to kind of show you how they work. You will not be asked to make this diagram or technically explain it in detail, but just for your clarity, one picture is better than 1,000 words. So whatever I've explained above, if you were not able to understand it fully, hopefully you can see a visual representation. Example: suppose we need to add 2 different 8-bit numbers. Now I've specifically added this example to make the concept more clear in your mind, because if you don't understand these 2 architectures, obviously you're going to have trouble in the other types of architecture as well. So we have the CISC approach. In a CISC approach, there would be a single instruction such as add or sum, and that would take 2 operands and add them together, store the result in ACC. Whereas in the RISC approach, the programmer would write the very first load. First of all, they would load the first number into ACC or into any other register. Then they would load the second number. Then they would use a suitable operator in order to add them, and then store the result by using a third or fourth command in a desired location or in ACC, etc. We are not going into too much depth. Like you don't exactly have to apply everything you learned in chapter number 4, processor fundamentals of AS. The add operation here is divided into parts, and this is where the concept of pipelining comes, namely operate, load, and store. Due to this, RISC programs are much longer. Like basically what happens in pipelining, maybe I should explain. Now that I've said it, I should give you a little clearer picture about it. Pipelining is you operate or you perform the first part of one instruction, like you load the values, and while you're loading it, in the next clock cycle you load the next instruction, and then in the next clock cycle when you are performing an operation upon it, you load the next instruction, and then you while you are storing the value for the first instruction, you start operating the second instruction, and so on. So although there is a little bit of time difference, technically one clock cycle difference between multiple instructions, but since computers run very fast, to humans it feels like instructions are being processed simultaneously. If you don't understand it right now, that's fine. It will come in a little bit of more description a little later on. So because of this, RISC programs are much longer because you are breaking every instruction into parts, and they require more memory to get stored, even though they require fewer transistors because the commands are less complex. Fewer transistor means technically less processing power. If this term confuses you, you can simply say they require less processing power but more memory or more storage. Here's a comparison between RISC and CISC, a big table. So technically you should learn any 4 points from it. Whatever you find easier. RISC focuses on software, CISC focuses on hardware. RISC uses only hardwired control unit. CISC uses both hardwired and microprogrammed control unit. Now, if these two terms are kind of confusing you, then again, rest assured you won't be asked to explain these terms in your paper. They are not directly part of your syllabus, but let me explain you for the sake of curiosity. Hardwired means like something that is embedded in the circuit itself by using hardware components arranged in a specific logic circuit, so it will perform some task, whereas microprogrammed CUs contain a software component or multiple instructions that work together in a specific manner in order to generate control signals. In RISC we use transistors, and in CISC transistors are used for storing complex instructions rather than being used as registers. In RISC we have fixed size instructions. In CISC we have variable size instructions. RISC can perform only register to register arithmetic operations, where CISC can perform register to register, register to memory, or memory to memory operations. We are talking about arithmetic operations obviously. RISC requires more number of registers because it needs registers to do its tasks, whereas CISC requires less number of registers as it can directly manipulate the values in memory. In RISC, code size is large. In CISC, it is small. In RISC, instruction executed always in a single clock cycle, whereas in CISC, it can take multiple clock cycles. In CISC, instruction is often of one word. In CISC, instructions are larger, more than one word. In a RISC reduced instruction set, instructions are simple and limited. In CISC they are complex and they use complicated addressing modes. In RISC Well, this is technically not really a difference. It's more like an abbreviation. It is reduced instruction set. It is complex instruction set. The number of instructions in RISC are less as compared to CISC, whereas in CISC, the number of instructions are more as compared to CISC. I know this sort of sounds childish and not really up to the level of A2. But hey, if you have a 4-mark question where you have to compare them, you have written 3 things and you can't think of a valid point for to score the 4th mark, well, you can easily fit this in. Okay, next we have interrupts. So what are interrupts? As you know, they are signals which alert the microprocessor that something has gone wrong, so the microprocessor can stop doing its current task and attend to the emergency situation first. They are essential for responsive and efficient system operation, because if we don't have interrupts in a computer, a lot of things will go wrong for a very long time, or we won't be able to prioritize things inside a microprocessor, like which task should be given more priority and which task should be given less priority. Now, how are interrupts handled in a CISC processor? The variety in instruction types and lengths complicates the handling process. If you have multiple interrupt sources, CISC processors would need a very efficient method to handle and prioritize multiple interrupts. Now, how it is done? First of all, you detect the interrupt. The processor continuously checks for interrupt signals, and after it has received an interrupt, it prioritizes it, or it detects its priority to determine the order of handling, especially if multiple interrupts happen simultaneously. Before addressing the interrupt, the current state of processor is saved, and then the ISR is called, interrupt service routine is called, which addresses the cause of interrupt. It tries to solve it. Once the ISR is completed, the processor is restored to its previous state and resumes its normal operation. Now, how would interrupt handling be done in a RISC processor? They have a more straightforward and faster interrupt handling processor, because they are optimized for quick saving and restoring of processor state. Processor saving and restoring processor state means whatever task you were working on, whatever were the values of the registers, they can be saved and then reinstated. So upon receiving an interrupt, the RISC processor quickly categorizes the interrupt type according to priority. Obviously, the processor then saves the current state and then runs the ISR, which is more efficient as compared to CISC ISR. After the ISR execution, the processor restores the save state and resumed its previous task. Pipelining in RISC. Pipelining refers to the process of overlapping execution phase of instructions to improve throughput, to improve time, to improve efficiency. The predictable and uniform nature of RISC instructions make pipelining much more easier and effective. So during pipelining, every instruction is technically broken down into 5 stages or 5 phases. The first one is fetch, then decode, then fetch the operand. The first fetch is for fetching the instruction, then the fourth one is execute, and fifth one is write back to the memory or to the register or etc. Hence, each processor unit must have access to its own set of registers. Obviously, initially only first stage of first instruction enters the processor. When it is done in the next clock cycle, second stage is started while also initiating first stage of the second instruction, and so on. So at the same time, you can handle multiple instructions. This allows processor to execute instructions in 5 times less time. This is a table to depict that. This is instruction fetch, instruction decode, operand fetch, instruction execute, and write back. Now we have 9 clock cycles over here, and we were able to perform 5 instructions in 9 clock cycles. As you can see from the table, in the first clock cycle we performed the first part of the first instruction. We fetched the instruction from the memory. Then in the next clock cycle we fetched the second instruction. Also we decoded the first instruction. In the third clock cycle we fetched the first instruction, we decoded the second instruction, and we fetched the operand for the first instruction. Then in the fourth clock cycle we fetched the fourth instruction, we decoded the third instruction, we fetched the operand of second instruction, and we executed the fourth instruction. In the fifth clock cycle we fetched the instruction, the fifth instruction, we decoded the fourth instruction, we fetched the operand of third instruction, we executed second instruction, and we wrote back the answer of the first instruction, completing first instruction overall. So technically the first, if I make a shape, if I highlight it, the first instruction technically took 5 seconds, but because of pipelining, because we simultaneously started work on second, third, fourth and fifth instruction, the overall time, if we go by this method that one instruction needs 5 clock cycles, then 5 instructions should use 25 clock cycles. Simple maths, right? But because of simultaneous working, we can completely solve. As you can see, this is the second instruction, then the third one. Yeah, don't mind, I guess I didn't draw it very well, but you get the idea of what I'm trying to circle over here. Then the then the fourth one instruction is completed in kind of like a diagonal state, and then finally the fifth one is completed. So overall 5 instructions were completed in 9 clock cycles instead of 25 clock cycles, reducing the time needed. That's why RISC processor needs a lot of registers, so they can do this pipelining. Initially we have kind of discussed all of that. Yeah, this we already discussed. Yes. So, benefits of pipelining: increased throughput. Pipelining allows more instructions to be processed concurrently or simultaneously, increasing the overall processing capacity as well as reducing time. That's our second benefit: reduced cycle time and efficiency boost, because you're doing more work in less time, so you're more efficient. Role of registers in RISC. Okay, so 15.1 is kind of a little big, but I would like to just finish it in one video, so hopefully you'll bear it with me. NA2, it's a little more difficult, it has to be. Anyways, so moving on, roles of register in RISC. They provide quicker access compared to memory, because as you know previously, the speed of RAM is about 10 times lesser than the speed going on inside your registers. RISC architecture often use load or store operations, where data operations are primarily performed between registers, not between memory and registers. So instruction is simplified and speed is higher. Extensive use of the registers enable effective instruction pipelining. As we have seen, the use of registers complements pipelining by providing rapid data access. Efficient register usage minimizes memory access. You don't need to go to RAM again and again, speeding up the process. Pipelining coupled with quick register access leads to faster and more efficient instruction processing. Challenges in the RISC architecture. Well, although pipelining is beneficial, it has two Drawbacks. A structural hazard or drawbacks of pipelining. It occurs when the hardware cannot support all the pipelined instructions simultaneously. Like I'm talking about the physical limitations of a process. There has to be a limit of how many instructions a processor can physically handle simultaneously. Obviously, this number cannot be infinite. Every processor has its own limit. Then we have the data hazard. What if multiple instructions need to access the same data or same resources? So, and you know very well, same data cannot be provided to two different instructions at the same time. Then we have a control hazard or a controlling problem. It happens due to branching instructions. Like if instruction is breaking into multiple more instructions, this can disrupt the flow of pipeline. How do we solve it? We use something known as forwarding. It involves passing data directly between pipeline stages, bypassing the need for it to be written and then read from registers. So instead of, if you know in the next instruction this data will be needed again, so instead of writing it back to the register, you just pass it on to the next instruction. Branch prediction. Technique to guess outcome of a branching instruction to maintain a smooth pipeline flow. Branching instructions are those where the outcome of one instruction is connected to one or more instructions. So if the processor is able to predict that the current instruction it is solving to what other instruction it will connect, then you can minimize a conflict. Then we have computer architectures. SIS, the first one is like a computer architecture is basically how you design your computer. SISD architecture, single instruction stream, single data stream. SISD architecture is the foundation of traditional computing system. Basically what it does, it executes a single sequence of instruction on a single data stream. At any given time, a single microprocessor works on a single data or a single instruction. This architecture is sequential, so you know it processes one instruction, moves on to the next, then next, then next, then next, and so on. So data is inputted, instruction stream is run, then data is outputted. The CPU fetches one instruction from memory, decodes and executes it into a single data element. This is a linear process, so it kind of limits the speed of computation, and technically over here we are not talking about code processors. We are talking about the pre-code processors where you could not have imagined solving multiple instructions simultaneously. SISD architectures are prevalent in general purpose personal computers like the Pentium series and so on. They are suitable for tasks that require sequential data processing like arithmetic operations and text processing. Or you can say technically inside a code processor like Core i5, i3, every single code is basically taking care of one single data stream and one single instruction simultaneously. Advantages, it has the simplicity of design, ease of programming and debugging. Disadvantages, limited processing speed and inefficiency in handling large parallel tasks. So to go a little up, we have the SIMD architecture, single instruction, multiple data streams. Over here, we can perform a single instruction on multiple data sets, the same instruction on multiple data sets. Like for example, the instruction says add, and you have 4 different values or 5 different values in the register. So when you apply the same instruction on multiple data streams, it will add all of them together, providing an output. This architecture is designed for parallel data processing, enhancing computational speed. It can perform same operation on multiple data elements, and for this you need special hardware like vector processors or GPUs. A normal processor cannot handle this. This is widely used in image and video processing. That's why I gave the example of GPU and vector processors, where same operation is applied to numerous pixels at the same time. It is essential in scientific computation, generating scientific models and machine learning algorithms that involve large data sets. Advantages, greatly increases throughput for data intensive operation where you have very huge data bank over there, time can be saved. Challenges: it is less flexible because you can only perform a single instruction to multiple data streams. You cannot apply multiple different instructions simultaneously, so only very specific parallel tasks can be performed by this type of architecture. It's not good for like any parallel processing task. Next we have MISD, multiple instructions single data stream. Now it is kind of the opposite of the first one, as single instruction single data, SISD. Over here we are performing multiple instructions on the same data set in order to and this is done by the use of multiple processors. It is a rare and specialized form of architecture. It is not commonly found, focusing on redundancy and error checking. So over here, different processors execute different instructions on the same piece of data. This setup is complex, but it offers unparalleled reliability and security in data processing. Predominantly, it is used in fault-tolerant systems where accuracy and reliability are critical, where you can say fail-safe systems, where you don't want any errors to happen, like maybe NASA's control room. You wouldn't want your $1 million satellite to just fall 3 minutes after launch, right? Examples include safety systems in aviation and critical medical equipment. Advantages: enhanced reliability and error detection, like errors are detection very quickly because you are performing multiple instructions using multiple different processors on the same data set. The difficulty or disadvantages: architecture is very complex and it has very limited use cases. You can't just get your hands on one and start using it for your games and something like that. You can only use it for specifically tailored machines. The last we have is MIMD. So basically we have two types of instruction sets and we have four types of computer architectures. Sorry, two types of instruction set architectures, four type of computer architectures. So overall we have about 6 types of architectures in this chapter. Multiple instruction streams means multiple instructions and multiple data sets. So you perform multiple instructions onto multiple data sets. They are very flexible computer architecture, and this is the most advanced form of architecture that we have. It allows multiple processors to execute different instructions on different data sets simultaneously. They can handle multiple tasks simultaneously because every processor is doing its own thing, making them incredibly efficient and very fast. Well, kind of like Ferrari of the IT world. They're scalable, so which means performance can be increased as you keep on adding more processors. Like if you set up a big server, you keep on adding more processors. The more processors you add, the higher your performance will go. This is an image to make you understand how it works. The first processor takes one data input and processes it, produces an output. Second processor simultaneously works on the second data input with a different instruction. The third one does that for a third instruction and a third data set, and all of them produces the output pretty much at the same time. This is ideal. This type of architecture is ideal for complex tasks like weather simulation, like scientific simulations, like if you're trying to simulate a black hole or some large complex biological processes, or something like large complex molecules, large scale scientific research and real-time data processing. These are commonly used in supercomputers and distributed computing system. They are not really available for everyday use because obviously they're very costly. Advantages: exceptional performance. Disadvantages: programming complexity. I mean, you have to be a super genius kind of a coder in order to deal with it, because the there can be many issues with synchronization between so many different processors, and as a coder you have to address them. Then we have parallel computer systems. A number of computers containing single instruction multiple data streams can be networked together to form a cluster. Like you can join them together so they kind of work like a hive mind. Well, I somehow can't really think of a better example, but I'm pretty sure you guys are familiar with what a hive mind is, where a group of fish, like those of you who kind of likes to read comics would probably know what a hive mind is. It's often there in almost somewhere in almost every superhero comic. But for those of you who don't really know, have you ever seen a school of fish swimming together as one? That's kind of like a hive mind, where a lot of people do something as a whole, as a team. So you can connect you can make a network of many SIMD, single instruction multiple data streams, computers or processors together in order to form a cluster, and this will form a very large pseudo parallel system that can act like a supercomputer. I am saying that can act because although it would be much faster than your average computer, it will obviously not be 100% replica of the performance of an actual supercomputer. This is known as grid computing as well. Now that you have a concept of what are parallel computer systems, then let's move on to the final thing in our 15.1. Massively parallel computers. They are formed by linking together a number of computers, typically tens and hundreds of computers together, effectively forming one machine with several thousand processors. And this is done because you want your computer to solve very complex problems, like probably maybe run a Bitcoin mining farm or run scientific simulations or complex mathematical models. Linkage of processors massively increases the processing power of the single machine. This is certainly different to cluster computers where each computer remains largely independent, but in a massively parallel processor, now this is technically a true hive mind. You cannot, the computers, the processor, they kind of lose their individual identification, and all of them work as one. Over here, each processor will carry out a part of the processing, and communication between them is achieved by interconnected data pathways. This is massively parallel processing, where this is a query. You give it to such a computer, it breaks it down, assigns it to multiple processors, and you get your answer in something like 15 minutes. Whereas in a single instruction multiple data streams architecture, or in a normal parallel simple parallel symmetric multiprocessing architecture, or normal parallel computers, it can still take a lot of time for doing something. Or in a normal computer, like this query is taking up something like 1 hour, whereas in a massively parallel computer, the same result can be achieved in just 15 minutes. So this concludes the topic and everything you need to know about types of processors and their architecture and the architecture of the instruction set. And then the last thing we have in 15.1 is the concept of virtualization or virtual machines. Virtual machines enable the operation of multiple isolated operating systems on a single physical host. As you can see, the back end is a Linux, whereas the front end, inside it I have two different windows open with two different versions of Windows operating system on a single physical laptop or on a single physical computer. This is achieved by the use of virtual machines. The separation between physical hardware and the software increases the computing efficiency, but it also offers improvement in terms of resource management, security, and flexibility. So we can use software to emulate or pretend or uh, yeah, pretend is a better word, to pretend other computer systems. Even like if you have a Lenovo laptop, you can use softwares known as emulators in order to, and you can install softwares which are exclusive for Mac systems by using your base hardware to create a virtual environment which appears to be that of a Mac. This emulation is known as a virtual machine, a software that enables you to run any other operating system or a software that that directly cannot run on your computer system. This process is known as creating a virtual machine. The process of creating and running a virtual machine is known as virtualization. The computer that runs the virtual machine is known as the host, and the virtualized system is known as the guest. Virtualization softwares known as emulators, they create a virtual implementation of the guest system on the host computer. It basically translates or bridges the gap between the lack of actual hardware and the software you're trying to run. The emulator translates the instructions of guest computers so the host computer can understand and execute them. It also provides a bridge that allows virtual machine to use the input-output systems, USB ports, and so on. Classification of virtual machines. We have system virtual machines. Okay, maybe I should give you an example of virtual machines. A very famous example of that is a virtual box that you can install on your computer system. Then you can install any an Android operating system on that, and then you can play any Android game, or you can download and play any game available on the App Store on your laptop or computer system. Okay, so classification of virtual machines. System virtual machines, they provide a comprehensive substitute for a real machine. Like if you cannot afford a Mac, you can just convert your Windows laptop into a Mac. They support the execution of a complete operating system. Then we have process virtual machines. They are designed to execute individual programs and often used as a platform independent programming environment. If you only want to run a specific single, like for example, I want to play Subway Surfer on my laptop, I don't need the entire the entire Android system installed on my laptop. So I can simply do that by using a process virtual machine. A role of virtual machines. They have enhanced isolation and security. They offer isolated environments for running multiple operating systems or applications. So they have a robust security mechanism. They are efficient and they use resource optimization, because obviously your RAM, your processor, they have to now be distributed between multiple operating systems. This leads to an enhanced utilization and optimization of hardware resources. Streamlining development and testing process. This allows developers and testers to have one single laptop with a lot of virtual systems installed, so they can test their product in multiple environments. Okay, you can argue that the result may not be 100% accurate, but at least they are something like 99 to 95% accurate. And you don't need to purchase a lot of physical machines. They facilitate server consolidation and cloud computing. As you know, they consolidate underutilized physical servers into fewer machines. They basically combine several servers on fewer laptops, fewer machines, which helps in reducing the hardware footprint or the hardware cost, energy consumption, and operational cost. They are foundational to cloud computing, where you can use less number of servers and you can virtually create more servers on top of them. So you physically have 3 machines, but you are able to run 4 or 6 or 8 servers on top of them. Benefits and limitations. This allows modern systems to use programs that run on obsolete and unsupported platform. Let's suppose you want to play a game from let's say 1980s, an arcade game. Now, obviously today's modern code computers cannot play them, but with the use of virtual machine you can. They allow platform independent programs to run on multiple platforms. Like you might have seen a movie known as Wreck-It Ralph, where the movie is about an arcade game, and with the help of an emulator or virtual machine, you can actually download it from the internet, Wreck-It Ralph game, and you can play it on your laptop. Yes, your Core i5, your Core i7, or your Mac laptop. They allow one computer to behave as several machines or several computers simultaneously. They can be easily backed up, they can be copied, and they can be reinstalled. Beneficial for corporate, where even if you lose one of your machines, you can just make a clone of it onto any other machine. Now the limitations on the drawbacks: they emulate software, not the hardware. They cannot magically create hardware out of thin air. So trying to use the full functionality of a specific software may cause problems, because if it drains too much resources like RAM, like processor, it may take a lot of time. Or the user may, or in simple terms you can say the user, although the software would run, or the game would run, the user may find that some of the features of it are not working, or they are taking a lot of time, or they are not working at all. For example, an emulation of a driving video game that requires steering wheel might not be able to operate the game correctly, because the software can emulate the game, but how will it magically produce a steering wheel instead of a mouse for you to use? It cannot make any changes. Virtual machines cannot make any changes to your existing hardware. So you'll have to somehow go to the market and magically hope that you find a USB enabled steering wheel like game controller. Emulation requires processing power and memory, because obviously a lot of translation is involved. Running a virtual machine may take a substantial amount of these resources, resulting in reduced performance from the host computer. If the host computer or the host system is not good enough, it doesn't have enough RAM or enough processing power, the virtual machine will lag and it will suffer from poor performance heavily. And that's everything you need to know in 15.1. I know this lecture got a little longer, but hey, all well that ends well. That's everything you need to know for 15.1. Hopefully you have understood everything. If you enjoy this lecture, give me a thumbs up, share it with your friends who are also giving computer science. Also, do give me comments. If you have any problem, any questions, any issues, write them in the comments below. I'll see you guys in the next lecture, and hopefully inshallah we'll wrap up chapter number 15 entirely. 15.2 would probably also be a little longer because it's about Boolean algebra. Anyways, take care. Allah Hafiz.